the chapter on determinants, will be discussing basics of theory of determinants. Our aim is not to calculate determinants of complicated looking matrices, but we want to understand how determinants are defined, what are the fundamental rules about determinants of matrices. Okay, so you have studied in school determinant of product of two matrices, product of determinants, and then using determinants, you have also you also know the formula for inverse of a matrix, yeah? And then Cramer's rule, and determinants. Determinant of transpose of a matrix is equal to determinant of the original matrix, and so on. So these are some basic facts, and we want to prove these basic facts or determinants without really using a formula for determinants. Okay, the formula will come out as a consequence of our discussion. Okay. Determinants of, you have seen determinant of 2 by 2 matrices, 3 by 3 matrices, and those are complicated looking formulas. You were just told this is the formula for determinant, but where it came from? What is the genesis of determinant of a square matrix? So determinants are associated with square matrices. If I have a n by n matrix, then its determinant will have n factorial terms. It's a very complicated function. Yeah? If the determinant, if we are computing determinant of a real square matrix, then determinant is a real number, and it's a function of n square entries of the matrix, and the formula has n factorial terms. It's a very complicated formula, and you might have wondered, no, why somebody came out with such a complicated formula and why it is so useful. Okay, so we will clear all these mysteries by treating determinants in a axiomatic fashion. You know properties of determinants. So those properties are, one of the properties that determinant of identity matrix is 1. It may look a trivial fact, but this becomes one of the defining properties of determinants. Similarly, if I take a matrix where two column vectors are identical, its determinant is 0. Or whether if two row vectors are identical, determinant is 0. And determinant is a multilinear function. It is linear in every column vector or every row vector. Okay, so we will take these three properties of determinants, which you know, as our characterization of determinant function. Okay, so let's approach in a axiomatic manner the theory of determinants. I'm sure you will enjoy this new way of approaching determinants. So let's begin. We set up axioms of determinant-like functions. Okay, and then we will prove the existence and uniqueness of this. We will prove determinant of product of two matrices is product of their determinants. Then invertibility of a matrix in terms of determinant. We will show that determinant is non-zero if and only if the matrix is invertible. Then we will compute determinant by Gauss-Jordan method. We used Gauss-Jordan method to find inverse of a matrix, but the same Gauss-Jordan method can be used to compute determinant. When I say Gauss-Jordan, we really mean the given matrix is being converted into row canonical form. Okay. If we do not insist on row canonical form, you just want to find the row echelon form, then it is called Gauss elimination method. Okay. But if you further continue and convert the matrix into row canonical form, then that method is usually called Gauss-Jordan method. We will find inverse of a matrix in terms of the cofactor matrix. Then we will approach Cramer's rule, which you know for 2 by 2 and 3 by 3 matrices for solving n linear equations in n unknowns. This is not an efficient method, but the formula is attractive, and you know this formula for 2 equations in 2 unknowns and 3 equations in 3 unknowns, but it is valid for n equations in n unknowns. And we will write down the formula for solutions of a system of linear equations where the coefficient matrix is invertible. That is called the Cramer's rule. Okay, so let's proceed to the axiomatic approach for determinant function. Yeah. So determinant of a 1 by 1 matrix consisting of one entry is A. Okay? And by convention, if a matrix has 0 rows and 0 columns, that means there is no entry. Then by convention, its determinant is supposed to be 1. Okay? It's just by convention. Determinant of a 2 by 2 matrix whose row vectors are AB and CD is AD minus BC. And then determinant of this 3 by 3 matrix has these 6 terms, right? So it becomes more and more complicated as the size of the matrix increases. Okay? So we want to approach the theory via their properties. Okay? So we will say that a function is a determinant function if it is acting on n by n matrices, where the entries are taken from some number system. The number system could be the system of real numbers or complex numbers or rational numbers. So f will denote a given set of scalars. Okay, it could be real or complex or rationals or some other field. Okay, so fix the set of scalars as f. Okay, f is for field. Then every n by n matrix where the entries are in this field of scalars, this function will be called determinant function if it satisfies certain properties. So suppose the column vectors of the matrix are a1, a2, an. We will think of determinant function or determinant like function as a function on the column vectors of the matrix. Okay. So we have space of all n by n matrices. So n is fixed, and then we are thinking of the determinant function as a function of the column vectors. So write the column vectors a1, a2, an. We'll define this function dA to be d of a1, a2, an. So there are there are n arguments in this function, and those arguments are ordered sequence of column vectors of the given matrix A. Okay. So this function is acting on the space of n by n matrices, and the output is a scalar in the field f. This is called a multilinear function. It's called a multilinear function if if every k and all scalars alpha beta, right, and these column vectors of the matrix and B and C are other column vectors. Look at the matrix whose column vectors are A1, AK minus 1. These are the first K minus 1 column vectors of the matrix. But the kth column vector is this linear combination of B and C. Okay, alpha B plus beta C. So B and C are column vectors with n components. And I take this linear combination of B and C. And the kth column vector of the matrix now is alpha B plus beta C. And then I keep the other column vectors, say K plus 1 an. The multilinearity means that I am fixing the other columns and I'm changing the kth column. Okay, and I take a linear combination of two column vectors. Then this is linear in this coordinate, kth coordinate. So it is alpha times dA1 AK minus 1B AK plus 1N plus beta times D of AK A1 up to AK minus 1C AK plus 1 AN. Okay, so alpha and beta they come out of the this function D. Okay, and we can separate B and C. Okay, so this is called multilinear property because this property is satisfied in for each one of the column vectors. Okay, this is the multilinear property. So D is called multilinear if we have this equation holds. That's the condition for multilinearity. D is called alternating if whenever AI equal to AJ, that means the matrix has two equal column vectors, then D of this matrix is 0. Okay, so alternating means two column vectors are equal, then the determinant of this matrix is 0. Yeah, then determinant of identity matrix is 1. So this we say this is the normalization property. Yeah. So it is giving a value to the determinant of identity matrix. Okay. There can be many functions which are multilinear alternating, but they are not normalized. So determinant of identity matrix may not be equal to 1. Yeah, for some multilinear alternative functions, we will come across those things. So focus on these three properties. So this function D is from the space of n by n matrices, and the output is a scalar. If it is multilinear, alternating, and normalized, then we say it is a determinant function of order n. Yeah. So there can be many functions on the space of matrices, but this function, which is multilinear, alternating, and its value on identity matrix is 1, is called a determinant function of order n. Okay, and we want to show that such functions are, there is only one function of this kind. Yeah, there is only one function of this kind, and it exists. So we have to show existence and uniqueness of determinant functions on the space of n by n matrices. Yeah. So let's prove a small lemma first. Suppose that D A1 A2 An is multilinear alternating function on the columns of n by n matrices. So I'm not assuming that its value on identity matrix is 1. I'm just saying that suppose we have a multilinear alternating function. Yeah. Then if some AK is 0, then D of this matrix is 0. So a matrix whose one of the column vectors is 0, then its determinant is D of A1, A2, An is 0. Yeah. Then if I interchange kth and k plus first column, then I acquire a negative sign. Okay. So this is true for any multilinear alternating function. Multilinear alternating function will satisfy this property that if AK is 0, then its D of that matrix is 0. And if I interchange two adjacent columns, then I acquire a negative sign. Okay. And the same property holds if I interchange ith column with jth column. Okay. Then a negative sign is obtained. All right. So these three properties, they are true for any multilinear alternating function. Proof. Suppose a column vector of A is 0. Then the 0 vector can be written as 0 times AK. But multilinearity will say that this scalar 0 comes out. Okay, the scalar comes out. So therefore, 0 times this scalar has to be equal to 0. So therefore, multilinearity implies part A of the lemma, that as soon as some column vector of a matrix is 0, then D of that matrix is 0. Yeah, we only use multilinear property. Then let us look at these adjacent columns, AK and AK plus 1, and we will interchange and calculate the value of D. So just for simplicity, put AK equal to B and AK plus 1 equal to C. Yeah. Then look at the matrix where the kth column is B plus C and K plus first column is B plus C. So we have two identical columns. Yeah. When we have two identical columns, by alternating property, D of such a matrix is 0. Right. But now I will use multilinearity in the kth argument and K plus first argument, and apply this multilinear property. So first split B plus C. So that gives me this, yeah, and this. So I'm keeping B plus C fixed, but B plus C I can split as B and C and use multilinear property. Now I will use multilinear property in B plus C. So then I will get when you split this using multilinear property of B plus in the K plus first component, you will get a matrix where two column vectors are B and B. That will be 0. And when I use multilinear property here in this component, you will get D of A1 AK minus 1 C and then C, and so that determinant that D will be 0. And so therefore, out of those 4 terms, using the alternating property, I just get that D, this is equal to D of A1 BC AN and D of A1 CB AN, and this is equal to 0. So that shows this property. that when I interchange two adjacent columns, then I acquire a negative sign. Okay. Now this trick can be used if the column vectors are not adjacent. Simply here I considered a matrix where the kth column is b plus c and k plus first column is b plus c. Yeah, I wanted to interchange k plus first column. I do the same thing to prove this fact. You look at a matrix where the ith column is ai plus aj and jth column is also ai plus aj, and then apply multilinearity, and you same trick will give you this. Okay, right? Okay. Now, with this experience, let us derive the formula for 2 by 2 matrices. 1 by 1 matrix determinant formula. You take a 1 by 1 matrix where determinant of a 1 by 1 matrix is the entry itself, and check that trivially it satisfies the three properties: alternating, multilinear, and normalization property. So determinant of 1 by 1 matrix has to be that entry itself. So let's look at a 2 by 2 matrix, and we use these three properties to show that determinant of a 2 by 2 matrix is uniquely determined, and it is the formula with which you are familiar. Okay, yeah. Right. So let's take a 2 by 2 matrix. So there are two column vectors, and we want to calculate determinant function. This is determinant function is alternating, multilinear, normalized on 2 by 2 matrices. Then we want to show that d of x, y, z, u is xu minus yz. So you know this formula. Now let us see how it is derived using these three properties. So what we do is look at the first column vector xz. So A1 can be written as xe1 plus ze2. E1 and E2 are the standard basis vectors. They are the standard basis vectors with two entries, and A2 has the entries as y and u. So A2 can be written as ye1 plus ue2. Okay, so I calculate the determinant function of this 2 by 2 matrix, where after writing A1 and A2, and we will use multilinear property. So d of A1, A2 is d of this and this. So there are two, it is a sum of linear combination of E1 and E2. This is another linear combination of E1 and E2. So I apply multilinear property in both the components. So I will first split ye1 plus ue2. So that is becomes ye1 and ue2. And I keep this fixed. Now I apply multilinear property on each one of these functions, and then I will get xe1 and ye1, but ze2 and ye1, that is the second term. Similarly, I apply multilinearity here, and so I get dxe1, yeah, xe1 and ue2, yeah, and then ze2 and ue2. Okay, now look at this. Here x and y, again by multilinearity, can be pushed out, and I will get d of e1 e1, but that determinant is 0 because two column vectors are equal, okay, e1 and e1. Similarly, this is also 0 by the same reason. So I'm just left with this term and this term. So you get yz d e2 e1, xu d e1 e2. Now this is obtained from this by interchanging e1 and e2. So it acquires a negative sign. So yz will acquire a negative sign. D of e1, e2, this by normalization property, this is equal to 1. And so this is equal to minus 1. And that shows it is xu minus yz de1, e2, but de1, e2 is xu minus yz. So we have derived the formula for 2 by 2 matrices simply by using multilinearity and normalization property and alternating properties. All three properties are used to derive this formula, right? If you don't use normalization property, what it says is that any function which is multilinear and alternating on 2 by 2 matrices is equal to the usual determinant times the value of D on identity matrix. Yeah. So once I fix the value of D on identity matrix, then this multilinear alternating function is determined. It is a multiple of the usual determinant. So any alternating multilinear function will be a scalar multiple of the usual determinant function on 2 by 2 matrices, where this factor is D of E1 E2. Yeah? That's why we use the term normalization, because we declare D of E1 E2 as 1. Okay. So then we get the formula for determinant of 2 by 2 matrices. Yeah? Any questions so far? Now it's clear that how to do this for 3 by 3 matrices. You can actually derive the formula for 3 by 3 matrices or 4 by 4 matrices, because I can play the same trick. If I have a n by n matrix, I will write every column as a linear combination of E1, E2, En. Yeah, every column will be written as a linear combination of E1, E2, En, and then I keep on, applying the multilinearity and alternating property, and at the end I will get D of E1, E2, En times some number. That number is the determinant. Okay. So we want to prove that determinant function is uniquely determined. Okay. It's clear now. For 2 by 2 matrices, we have proved that determinant function is uniquely determined, because we have found that function as a function of x, y, and z, u. So for 2 by 2 matrices, it is clear now that there is only one function on the columns of a 2 by 2 matrix which is alternating multilinear and normalized. Yeah, and you, with similar technique, you can prove this fact for 3 by 3 matrices. Yeah, but we want to prove this for n by n matrices, not by computation, but by a concept